Okay, so welcome to the part 2 of the A-level content for circular motion, and we've just looked at some theory surrounding the conical pendulum, and we're now going to have a look at a couple of examples related to this. So first example tells us here an inextensible light string, so we know that there's no elasticity in the string, it has no mass of itself, it's 50 centimetres long, it's attached to a fixed point A that's 30 centimetres above a smooth table. The other end is attached to a particle of mass 3 kilograms at point B, and the particle is moving in a circle supported by the table with the string taut. So this is actually resting on the table, and the first thing we've got to do is find the value of the normal force exerted by the table on the particle when it's moving with speed 10 centimetres per second. So what I want to do first of all is draw my little diagram, as always. So I'm going to have a think. It will be based on that conical pendulum, so I know that I've got my string. So start with our right angle triangle. This is my string here. I know that that is 50 centimetres long. It's attached to a fixed point A, so that's A. It's 30 centimetres above a smooth table, so here is 30 centimetres. I know that it's attached to a particle of mass 3 kilograms at B, so here's B. So that must be 3G there. It's resting on a table, so this here is resting on a table, so I've got my normal reaction force. You could use R if you wanted to, it doesn't really matter. I also know that I'm going to have tension in my string in that direction. And I think that's it in terms of the forces. So let's have a think about what we can actually figure out here. So I know that I can look at the acceleration towards the centre. So I'm going to start with that. Let's figure out what that is. So that is this. In this situation, I'm going to use, I've got my choice of R omega squared or V squared over R. Well, I'm not told omega, I don't know the angular speed, so I'm going to use normal speed here, so I'm going to use V squared over R. So that's 10 squared over 40, which is 2.5. I'm then going to do those two components that I did before. So resolve vertically and resolve, well, not resolve horizontally, but apply Newton's law horizontally. So because I've worked out my acceleration, I'm going to go horizontal first. So horizontally, I've got F equals ma. So F towards the centre here. I've got F. Now I haven't put in, actually, let's put in my diagram that is alpha. So I've got T cos alpha is equal to the mass, which is 3, times the acceleration, which is 2.5. If I have a look at cos alpha, now if I go back to my diagram, I've actually got here a right angle triangle, and I've got my opposite over my hypotenuse for sine alpha, and I've got my adjacent over my hypotenuse for cos alpha. I've just realised that I didn't speak to you about where this 40 came from for the R. So if we go back here, just for the radius, I can use Pythagoras on this triangle to say that my radius is 50 squared minus 30 squared. If you pop that in your calculator, you will end up with 40, but you should be able to spot that this is actually a Pythagorean triple. So it's a 3, 4, 5 triangle, but obviously just multiplied by 10. So that's where that 40 comes from. And equally here, we can use that for our cos alpha. So if we go back to, we've got T, cos alpha is adjacent over hypotenuse, so that's 40 over 50, and that is equal to my 3 times 2.5. If I rearrange that, and again you can pause and have a little go at it yourself, you'll see that you actually get T is equal to 9.375. So that is the tension in the string, but actually the question is not asking me to find the tension, the question is asking me to find the value of the normal force. But so far I've only dealt with my horizontal situation. So if I resolve vertically, again, let's go back to my little force diagram here. Upwards, I've got N, my normal force. plus t sine alpha, and that is equal to 3g. N is what I'm trying to find. T I've worked out is 9.375. Sine alpha, and go back to my diagram here, sine alpha is opposite over hypotenuse, so 30 over 50, and that is equal to 3g. Again, there's quite a bit to rearrange there, but I want you to pause, have a go at it yourself, see what value of n you get. I'll pause for a second and then tell you what the answer is. So you should end up with n is 23.8 newtons for the normal reaction. So again, you've seen how we've applied those two sections of the horizontal using Newton's second law and then resolving vertically. So let's have a look at another scenario, part 2, which is asking us to find the speed at which the particle is moving when it's about to lift from the table. So if we go back then, I'm just going to shimmy down here. If we go back then for part 2 and look at, again, acceleration towards the centre. I know, as I said, it's v squared over r. Now, v is what I'm trying to find. I know that r is 40, so it's v squared over 40. Exactly the same principle. So let's look at horizontally. So F equals ma. Same as before, horizontal force is T cos alpha. That's equal to our mass, which is 3. Our acceleration, we said, is v squared over 40. Again, we can substitute in what we know. We don't know T in this situation yet, but cos alpha we can write in, which is 40 over 50. 3v squared over 40, and that implies then that our tension is 3v squared over 32. So now then, let's resolve vertically. So again, same as before, we had n plus t sine alpha is equal to 3g. Now, in this situation, it told us that the particle is about to lift from the table. So if it's not touching the table, we know that actually there is no normal reaction. So we can say that n is 0 as mass is just lifting off the table. Okay. So I can put in 0 here. T I've worked out is 3v squared over 32. Sine alpha we worked out from previously is 30 over 50, and that is equal to 3g. So again, you've got an equation here to rearrange to find v equals. I'll pause for a second so you can work out v. And you should get that v is equal to 22.9 meters per second. So if you haven't got that, have another work through, but you should hopefully have got that value. Okay, so we move on now to example 2. And again, we're going to apply those same principles of the conical pendulum. We're starting though with a different scenario where we're looking at a fairground ride. And hopefully you've seen these kind of things or seen pictures of them. Here's a picture of one in real life. Here's a sort of simpler drawing where you've got a axis rotating here, vertical axis, you've got arms coming off, and then you've got a string or a chain coming down holding a chair. This is a very simple sketch of a sideways view, so that's your axis of rotation. And if we have a look at the example here, it says that the arms rotate, people sit in a chair. The chains are 2 meters long, so that's the chain there, and the arms are 3 meters long here, and we can see that the rotation is 1.1 radians per second. So that just sets the scene for this situation. And if we then have a look at the example here, we can see that, let me just have a look at my question. For example 2, it's asking us to resolve in that same direction. So we want to just have a look at the angles. It's saying find the angle that the chains make with the vertical. So if we go back to that diagram that we had right at the start, I'm just going to draw it in a smaller version here. So you've got our axis of rotation, you've got the arm, you've got the chain. We know that that is 3, that is 2. We want to find the angle with the vertical. I'm just going to draw this in here. And so we can see as well here, that's our angle alpha, is what we're trying to find. We know we've got a mass down here of mg. If we want to know this distance here, because we're essentially going to need our radius at some point, we'll have a look at what this distance is. So this section here is going to be 2 sine alpha using this triangle. Again, pause and figure that out if you need to. So we can write down here that the radius of the whole thing, so this total distance there of the circle, so imagine this is spinning round, causing a circle, so this distance is 3 plus our 2 sine alpha. So we're just setting this up. We know then that the acceleration, which is our omega squared, we're told omega in the question, so that's going to be 3 plus 2 sine alpha times 1.1 squared. That's our acceleration. If we want to evaluate this, that would be 1.21, 3 plus 2 sine alpha. Again, same principles. We're going to go horizontal first. So F equals ma. So we know that our force, which is T, oh, I haven't put my tension on the chain, so let's pop that on the diagram here. So put the T on. I was wondering where my force had gone. So if we have a look at the horizontal direction, it's going to be T sine alpha, and that is going to be equal to m, and our A is up here, which is 1.21, 3 plus 2 sine alpha. So I've got an equation here, that's my equation 1. If I look vertically, and I'm going to resolve, remember, vertically. So again, go back to my diagram here. So T cos alpha is equal to mg. So I know that T is equal to mg over cos alpha. That's my equation 2. And if I substitute my equation 2 into my equation 1, let's see what happens there. So I end up with mg over cos alpha sine alpha is equal to 1.21 m. Just shorten that there. 3 plus 2 sine alpha. I can see that my sine and my cos here would form a tan, and also I've got an m on both sides, so I can cancel my masses. So I would have g tan alpha is equal to 1.1 times 3 plus 2 sine alpha. Now at this point you'll notice that I've got 2 trig functions here. I haven't got the ability at the moment to actually solve an equation like this. So frustratingly, actually what we'd have to do at this point is use numerical methods. So use different number methods on your calculator to try and work out. It's a bit fancier than trial and improvement, but essentially that's something that you'll come across later on. So use numerical methods. And you actually end up with alpha's 25.5 degrees. And you can have a look at that, see if that works. You can plug that into that equation and just check. This point, it's not so much worried about getting that final answer. It's about knowing that method for this section.